Good afternoon, students. Welcome back to our digital series electronic classes. That is nothing but we are going to continue our digital signal processing classes. That is nothing but digital classes. In today's class, we are going to continue the concept of the approximation methods what we had in IIR filter. What is IIR is all about? Infinite impulse response filters. In the previous class, we have discussed what is the definition of IIR filter. What is IIR filter is all about? It is a recursive type of filter. It should have bounded input, bounded output, and should be having the impulse response. H of n, mod of h of n should be less than infinity. That indicates what? It is what? A realizable filter, which can have the functions, which can we get the functions by taking that h of n. And we have seen different types of filters. What is the filters is all about? A electronic device which allow the certain band of frequency which should have attenuation of unwanted signal and should will pass a certain part of frequency components. That is nothing but it should consist of two types of band. One is the pass band and then there is the stop band. By looking into its frequency selective nature, that means it will select a part of frequency, it will reject the remaining part of the frequencies components. So this is done by using the filters. So we have discussed about low pass filter, high pass filter, band pass filter and band stop filter. So these types of four filters we have seen by seeing its two things. What is the two things we have discussed? We have discussed about the pass band and stop band. These things we have seen. So now what we are going to what we are learning in today's class, we are going to learn the approximation techniques. By using those filters, how the approximation techniques can be used to design the IIR. So in today's class, we are discussing unit 2 topics, that is nothing but IIR filters. So in that, we'll be having two types of approximation techniques. One is Butterworth approximation techniques. Second would be Chebyshev approximation techniques. So in first one, we are learning Butterworth approximation. Second one, Chebyshev approximation techniques. So these are two techniques which we are learning in unit 2. And we want to design the filter and the order of the filter we want to find out. What is the attenuation in pass band? What is the attenuation in the stop band? What is the frequency of pass band? What is the frequency of stop band? Even the critical frequency we will take it and then we will design the IIR filters. So what is the things we are learning in IIR filters? We are learning Butterworth approximation and Chebyshev approximation. These all are what actually these are nothing but when we had any kind of filters. What did filters should have? It should have attenuation alpha. Alphas are of two types because we are learning how many types of bands? Pass band and stop band. Alpha P and alpha S. What is alpha P means? Attenuation in the pass band. Alpha S is nothing but attenuation in the stop band. Likewise, if you want to see the frequency component omega, it also are of three types. One is frequency in the pass band omega P, critical frequency omega C, then frequency in the stop band omega S. So for frequency components omega will be having three types of frequency. Second one, attenuation factor. Attenuation factors are what actually? The unwanted signal you will try to eliminate it. That can be done by looking into its attenuation factor alpha. In attenuation factor alpha, it consists of two factors. One is alpha P, that indicates what? Attenuation in pass band. Alpha S, that indicates attenuation in the stop band. So these two things we just want to consider and these three frequency component we need to consider. The next thing what you need to understand, we need to understand the Butterworth approximation are of two types. One is analog Butterworth approximation, the next is digital. So in order to understand this thing we need to go for order. What is this N indicates? It indicates what is the order of the filter you are using. Whether using first order, second order, third order, fourth order. There should be a specific order of the filter we should use it in order to find out what type of filtering you are going for it. So for that reason we need to understand what is this N. N is nothing but order of the filter. So to find the order of the filter by using Butterworth approximation we will be having one particular formula. N values is nothing but its integer. So N always greater than or equals to, we had this particular formula for finding the Butterworth approximation. What is this Butterworth approximation techniques? It is used to find the filtering of infinite impulse response in such a way that the order, first thing we need to find order. After getting this order we can find out what type of filter we are going to design. So in order to do this thing, in order to achieve this approach, we need to get alpha p, alpha s, omega p, omega c and omega s. After knowing these parameters, we can find out the n. So what is n actually? N is log of under root of 10 power 0.1 alpha p minus 1 by 10 power 0.1 alpha s minus 1. This is the log divided by log of. So what we are doing? We are finding the order of the filter. How do we find order of the filter? 10 power log of 0 alpha s minus alpha p. This is alpha s minus alpha p by. So what is this alpha s indicates? Alpha s indicates attenuation in the stop band. Alpha p indicates attenuation in the pass band. So first 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 divided by frequency in the stop band into divided by frequency in the pass band. We will take logarithmic factor and we will find out that value. So what we are doing? Alpha s by alpha p. So we have taken alpha s by alpha p. Now we will take the frequency. What is the frequency? Omega s by omega p. What is omega s omega p? Will state that it states that frequency in the stop band, frequency in the pass band. If you use this formula, this particular formula, you can find out the order of the filter. So what we are finding now, students, we want to find the order of the filter. In order to get the order, what we are doing? We are using attenuation of pass band, attenuation of stop band, frequency of pass band, critical frequency. What is a critical frequency? A frequency, what is called? It's like a barrier between your pass band and your stop band. A point or a frequency. After that, certain band of frequency will be rejected. Before it, certain band of frequency will be allowed. That depends upon what kind of filtering you are doing. Whether you are doing low pass filter where the lower component has been passed and the higher component will be attenuated. Depends upon the critical frequency. After the critical frequency, all components will be stopped or rejected. So that depends upon your critical frequency. Likewise, stop band frequency. By knowing these factors, we can substitute here and we can find order n. N value is greater than or equals to this all factor. They'll give in the question alpha s alpha p, omega s omega p. So we need to substitute in n and we need to find the value of integer. So what is n indicates? N indicates always whatever the value of n we want to find, whether it is greater than or equals to. Depends upon greater than or equals to value, we will find out the value of n. So what is n? Log of 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 by frequency in stop band divided by frequency in pass band. So by knowing the frequency, we will find out its factor of integers. So how do we find the factor of integers? We will put the values to it. In exam, they'll give the value of alpha s, alpha p, omega s, omega p. These value we can substitute and we will get the value for it. So how do we get that value? We will assume some integers. Directly we cannot solve it. For that, what I am doing? I am assuming some integers. What integers I am assuming? So see, students. So see here what we had this factor. Suppose this is your factor. So this factor I am assuming like epsilon. Epsilon is equals to 10 power 0.1 alpha s minus 1. This is your epsilon. This I am saying some other alphabet lambda. This is my assumption. This is the assumption what we are doing directly. You can put it this value, but or else if you want to simplify, you can do it. This I can write 10 power 0.1 alpha p minus 1. So by substituting this thing, what I can write? I can write order of the filter will be make it as n greater than or equals to log of this log of this is what? Root of what is root? What is this value? Epsilon by lambda. This we had divided by log of omega s by omega p. This way also you can write the order of the filter. Okay, so after getting the order, next thing we had alpha p, alpha s, omega p, omega x. Next thing we need to get the critical frequency. How do we get the critical frequency omega c? For that also we have to use certain formulas for Butterworth approximation. That formulas we will see. Before doing this critical frequency, first you make a note of this particular order of the filter. So students, so we found the value of n. So in this one, what actually we are doing, we found till now the order of the filter. That is, order of the filter is given by n is greater than or equals to log of under root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 divided by log of frequency in the stop band by frequency in the pass band. So this part we have written. So what we found now, students, so we found what is alpha s is all about. Alpha s is, what you can write for alpha s? Attenuation in stop band. Alpha p is attenuation in pass band. Omega is frequency in pass band, radian per second. This is for stop band frequency. What about this one, alpha omega p? Pass band, radian per second. So this I can write it down. So I wrote all these values. Next thing, for Butterworth filter, what actually thing we are doing? We just want to find order of the filter. After knowing the order, next criteria is to find what? We need to find critical frequency, omega c. So how do we find critical frequency omega c? Omega c is equals to, if you looking into the pass band, so we can write omega p by 10 power 0.1 alpha p minus 1 whole power 1 by 2n. What is this capital N? Capital N is nothing but order of the filter. What order we are finding in the previous one? The same order. We will substitute here and we will find the cutoff frequency omega c. So we got order, we got omega c. What is the next criteria? To find the transfer function. Or transfer function is given by h of s. When we are finding h of s at omega c is equals to 1 radian per second. So we assume omega c is 1 radian per second. We will find the cutoff frequency. So next thing, we should know the poles. What is the meaning of poles? Poles are nothing but whenever we draw any particular graph, like you're drawing one graph like this. So when you are saying x-axis, these are called zeros. When you are saying the y-axis, that is nothing but your poles. So we just want to find poles. We are giving by letter phi. Okay, so we want to find the pole. How do we find pole? For finding the poles of the Butterworth. So that is given by s is equals to omega c e power j phi k. So this is a formula to find the poles for any particular Butterworth filter. So we'll see the steps. So what we are doing till now, we can conclude by seeing that we do have to find order of the filter by looking into the value of attenuation in stop band, attenuation in pass band, then omega c and omega p. By looking into these two parameters, we can find the order. After knowing the order, we can find the cutoff frequency. After knowing the cutoff frequency, we can find the transfer function, then poles. This is the way we can find. Now we'll see the steps to design the Butterworth filter. So before doing it, just see this one. What actually we are doing. If you just want to note it down this complete part, then I'll go for next part.